Howdy everyone, I'm Biscuit and I'm back with another video after a little bit of time, but today we're going to be deriving my favorite formula. It's called Euler's formula. If you haven't heard of Euler, he's basically the greatest mathematician of all time. In his heyday, he essentially created every mathematical field or revolutionized an old one, so his fingers are basically everywhere. I mean, basically how mathematicians it goes like, people on the level of Newton, and then no one, and then Euler. I mean, he's just on a completely different level. The joke is that, we have to name everything after the second person who found it, because then everything would be just named Euler at that point. But today we're going to derive Euler's formula, and essentially that makes a connection between exponential functions, so the ones go really fast, and then trigonometric functions, which go woo and stay in this little bit area. And it's really crazy that they have any connection at all. So the most straightforward way to show this is actually going to be using something called Taylor series. Now, Taylor series is a way to write out a function as a sum of infinite number of polynomials. So it ends up, it's a crazy idea. It ends up being really helpful in computational stuff, physics and engineering, because sometimes you only care about a few number of these terms, but we'll get into it later. But what we want to show today is going to be much more obvious using them. So here we have the Taylor series for an exponential function. If you noticed, it calls it a Maclaurin series. So Maclaurin series is just a Taylor series expanded around the x equals 0 point. So that's the thing with Taylor series, that you always need to expand around a point, throw up a graph of why that makes sense. If you use a certain number of terms, it's closer and closer, but it's exact at that one point. But anyway, let's go and yoink this. Okay, now that we've yoinked this Taylor series, I'm going to write it out to a certain number of terms. I mean, we can sort of see where it's going after a little bit. So the two functions that we have to care about are sine and cosine here. If we look at them, almost if we combine both of them, they almost kind of look like the exponential. Sure, there's a few minus signs wrong and some stuff, but we'll fix that all in the end. But let's go yoink those two. So we yoinked them and we're looking at them, they're kind of similar, but there's still a bit of difference with signs. But what we're going to do is not look at an exponential, but a complex exponential, and this is going to fix our problem. So let's write out what that looks like. So if we instead write a complex exponential, we put an I. I is the stand-in for the square root of 1. We use it for imaginary numbers. Instead, expand around that, so every time we see an x, we'll put an ix instead. Let's see what we get. Okay, so here I've actually, pushed all the i's through. You can see we get something that's pretty interesting here. So we notice that we'll get a 1, just like the cosine. We'll get negative x squared over 2 factorial, just like the cosine, and then x to the 4th, just like the cosine. So it looks like we can actually just write out the cosine is going to be straight up part of this. But so for the sine, we get something a little bit different. So instead of an x, we get an ix. Instead of the x cubed, we get an ix cubed. Instead of the x to the 5th, we get an ix to the 5th. So we can see sort of this is going to go. We have a number of terms that are exactly the cosine. Then we have a number of terms that are almost the sine, just times multiplied by an I. So let's write that out. This is implying that e to the ix equals cosine x plus I times the sine of x. And that is Euler's formula. I mean, that is the connection. I mean, this is a crazy connection. We have a function here, an exponential, that blows up, goes really high, goes really fast, being connected with two trigonometric functions, which stay in a small little zone. But the thing is, it's a complex exponential. It changes it a little bit. So we're going to be able to do a few things, show a few interesting things with this. We'll keep going with this idea. So one thing we'll be able to do is show my favorite equation, which connects 5 of the most fundamental units or the constants ever into one cohesive equation. It's crazy they all fit in here. But for x, let's just put in pi and we can get that. So we get e to the I pi. We get cosine of pi plus I sine of pi. So if we're assuming radians, the cosine of pi, well, that's just equal to -1. So write that in. So this is just equal to -1. And then sine is equal, well, sine of pi is just 0. So let's get rid of that. So e to the I pi equals -1. So we'll take it one step further just to get more constants in here. Let's just move the 1 to the other side. So we have e to the I pi plus 1 equals 0. So we have to sit back and think about how crazy it is that we have all these constants, all 5 of these most fundamental constants in one equation that makes sense, and it's not just multiplying by 0 and copying out. We have e, so this has to do with continuous growth. So if you have a loan that continuously compounds, I mean, that's what comes in, an exponential comes in. Then you have I, which has to do with roots and imaginary roots specifically of, quadratics and other types of polynomials. Then we have pi, which is to do with circles. And then we just have 1 and 0. And we know how important those are. You add 0 to anything, you get the same thing. You multiply 1 by anything, you get the same thing. I mean, this is crazy. They all end up in the same place. What the heck? So the connection between complex exponentials and trigonometric functions goes pretty deep. I mean, you essentially can take this formula and write trigonometric functions out in terms of complex exponentials and, back and forth. So let's quickly show how you can write a trigonometric function in terms of complex exponentials. So we put an e to the I x, instead of positive here, we'll get cosine x minus I sine x. So we can use the combination of these two to, essentially get rid of one of the trigonometric functions, and we'll just get 1 at the end. So let's take these two equations and add them together. So if we get that, we get e to the ix plus e to the I negative x equals 2 cosine, because the signs go out if we add them together. So you can see that cosine x equals those two complex exponentials added to each other divided by 2. And there's our connection. So that's one way you can just write out cosine x. And actually, this is a way a lot of people actually prove a lot of trigonometric identities. If you've ever seen in a big Wikipedia article, like I usually do, trying to solve problems or whatever, you'll just see just right out, oh yeah, obviously cosine cubed equals, tangent to the 4th. I mean, how do you know these sort of things? Well, you can write them out as complex exponentials, and the algebra is always a bit more obvious when in that way compared to trigonometric functions, which are, opaque and really hard to understand. But, what happens when you multiply exponential by something or square it. It's much more obvious compared to trigonometric functions where you have to just memorize a ton of stuff. And just for completeness sake, let's get sine and write that in terms of complex exponentials. You get that by subtracting. You see, you get rid of the cosine and stuff. E to the ix minus e to the negative ix equals 2I sine x. Okay, and then you can get sine of x by dividing all that stuff the other side, and you're good. So sine is just those two things subtracted divided by 2i instead. So you can use any combination of these, they're interchangeable, no problem. So I want to go one step further. I want to show fundamentally that these have to be related to each other in a completely different way. And this is, so far we've been talking about math. I mean, this is technically not supposed to be a math channel. We'll talk about it sometimes, but this is supposed to be a physics channel. So let's do a physics problem. Actually, probably the most fundamental physics problem you could do, and that's a simple harmonic oscillator. And so you may know the solution from this if you've done it before. You're going to get trigonometric functions, but you can get complex exponentials too. They are a solution. So let's see that. So here we have a differential equation for a simple harmonic oscillator. And sometimes, if you've seen this, sometimes it's just called Hooke's law. So what is this representing? So essentially, this is representing the motion, the acceleration of a block that's connected to a spring. And if I take the block and I move it just a little bit, if I move it off some equilibrium point here, I move it an x amount in this direction, maybe this is the positive x direction, then I'll feel an acceleration the opposite direction, that's this term here, essentially equivalent to that amount, as proportional to how far I drag it away. That's essentially what this differential equation is saying, to some constant. And this x is meaning that the acceleration, I'm always being pulled in the opposite direction as I'm pulling out. That's what a spring does. I move in this direction, it pulls me back this way. So what does this mean? So we need to solve this equation. We can figure this out by experience. Maybe we've seen this before, maybe we're not. Essentially what we're asking with differential equations is we have some function x, it's a function of time. Which function do I put in for x that will make this statement be true? So what function, if we know a little bit of calculus, what function when we take two derivatives of it gives it back the same function just times some constant and a negative sign? So with our experience with calculus, we may remember a trigonometric function solves that problem. If I take two derivatives of a trigonometric function, I get the same thing with a minus sign, and maybe I get some constants out front in the end. But instead of using trigonometric functions, so here's the big point, here's the big thing here. Instead of using trigonometric functions, I could use complex exponentials instead. And this is actually a lot of times what we do in physics. Sometimes it's really nice to work with complex exponentials. So let's do it here. We'll plug and chug, throw it in, see what happens. We'll show that the sum of two complex exponential functions also is a solution to this. So now x of t is going to be a1, some other a1, you know, it doesn't have to be the same one, I kappa x plus a2e I negative kappa x. So let's plug this in here. What happens? What do we get out in the end? So all we need to do is take two derivatives. Fortunately, it's really easy to take derivatives of an exponential because you just get the same thing back times the chain rule. It's almost like that's like trigonometric functions with some negative sign. But okay, what happens when we take two derivatives? Well, all we're going to do is do the chain rule down. We'll bring down I kappa twice. So I kappa squared is going to be negative kappa squared because I squared is -1. Straightforward. You get a1, get that negative sign, kappa squared, e I kappa x. Looking good so far. Same thing over here. We'll bring down negative I kappa k, negative I kappa squared. That negative sign goes away. The I squared gets us another negative sign, kappa squared, e negative I kappa x. And then we look at the other side. That's the same. I'm not going to write that again. Wait. I don't have to write it again. There it goes. Okay, we're good. So that's the same thing. Same thing. Valid solution. So I can solve this differential equation with either set of functions. I can solve it with trigonometric functions, or I can solve it with complex exponentials. And so this is the equivalent of having a coordinate system, you know, that's pointed this way. I have up and down and left and right here, or I can shift it. And instead of, you know, different sets of coordinates or vectors, I'm using different families of functions, but they are equivalent to each other. So there's no problem with using one or the other. I can always exchange between the two families in the end. So I think that's about it. Thank you so much for joining. I mean, I haven't uploaded in a while, but the support has been absolutely crazy. I can't believe we have had so many people watching and subscribing. So thank you for doing all that. Thank you for coming and watching. Hopefully you learned something. If you have anything to say, any comments or corrections or maybe future video ideas, you know, tell me in the comments below. But, you know, thanks for watching. Okay, thanks, bye.